So here's our second approach that is algebraic for solving systems of linear equations, and it's called the addition method. Some resources call it the subtraction method. Some people call it solving through elimination. Really, they're all about the same thing. It really is the best method when all variables have coefficients. We're going to end this section with looking at systems of equations and then deciding how would you want to solve them. Remember that you have the three options. So 8.1 was all about solving through graphing. So we had the first option where you had the consistent system. So we said that was consistent. And we had the answer of x and y. In the second reality, we had that case where you had two different equations and they might look different, but they actually were the same line. And in that case, we said that that system was dependent. And they also share the same line and share that infinite number of solutions. The third case, you would look at the two lines and solve by graphing, we would see that we had two parallel lines. And so this is that sad case where there's no solution. We say that it's an inconsistent system. And there is no solution for this. There's no point where these two lines intersect. There's no values of x and y that actually satisfy both of them. So I often think that these are the easy to please ones. These ones are the hard to please ones, sort of turning them into personalities. So that's where we started with chapter 1 in this 8.1. In 8.2 and 8.3, with the algebraic approaches, we are looking for different things. And so in a consistent system, you'd solve for each of the variables. Oops, solve for x, then solve for y, or y then x, whatever, and so that you get both of them. In a dependent system, when you're solving through algebra, this is where you got down to that line of truth. Whatever that truth was, 2x plus 1 equaling 2x plus 1, 3 equaling 3, 6 equaling 6, whatever it was, that was your evidence that it was a dependent system. The last one here was a line of garbage. It was a line of untruth. It was a line of nonsense, like 3 equals 6 or 0 equals 2 or whatever it is. In that case, that would be your piece of evidence that tells you that your system of linear equations is actually inconsistent. So these are the answers. I put a box around truth by accident there. So you have your line of truth tells you that your answer is a dependent system. Or your line of garbage tells you that your system is an inconsistent system. Okay, so going on to this last algebraic approach here, this solving through the addition method, there are, kind of words here. I find that sometimes it's easier to show you, not tell you. The idea here is that we do have an objective. The objective is to eliminate one of the variables, kind of like what we did when we were subbing one equation into the other. We're going to start by numbering the equations, which we've done before, and then you're going to add with the vertical method. If you remember that back from when we did the polynomials chapter, the idea with this is that one variable should disappear like magic. Again, I think it's easier for me to show you as opposed to tell you. It might be worth putting your own words or annotating one of these examples. Okay, so here I have my first system of linear equations. I have equation 1 and equation 2. With these ones, this whole page is primed to just work. And so if I were to solve this by addition, I'm going to take and add those two vertically. If I add these two vertically, I have an x and an x, so that's a 2x. Take a look at what happens to the y variable. I have a positive y and a negative y. That one disappears. And so now we have equaling 8 plus 2, 10. I've eliminated my y variable when I added these two vertically. That's what those instructions are trying to tell you. So solving for x, I would divide by 2 on both sides, and I get that x equals a 5. Now I can take this and sub it back into any equation I want. So when I take a look at this, I'm going to say, I'm going to sub that into equation 1. And when I do that, it's going to look something like 5, and you can sub in with brackets if you want, plus y equaling 8. In this case, I'd subtract 5 from both sides, and I'd get that y equals 3. And again, this one would be a consistent system. It would intersect at the point 5 and 3. So we've got a consistent system here. Let's take a look at C. And again with C, like I said, this whole page is rigged to just work. So we're going to take these two equations and solve through the addition method. So we're taking these two and adding them vertically. So I'd have x and x, so 2x. And again, this case, I go negative x and negative y and a positive y. Those wipe each other out. So I can just ignore them. It was 0y. And the numbers out the end here would give me a 4. So negative 2 plus 6 is 4. I can then solve for x, so that I get x equaling 2. Only halfway done with this, and you can choose either of the equations. I didn't number them. I think I would choose to sub into equation 2, mostly because it has no negative signs in it. So I'd have 2 plus y equaling 6, and you could sub in with brackets. I'd subtract 2 from both sides so that y equals a 4. And again, putting that together as an answer, it is a consistent system. And 2, 4 is the point where those two lines would intersect. The 2 and the 4 are the values of x and y that would satisfy both of those equations. All right, 2 more to do here. We are solving through the addition method. So you take these, and what should happen is one of the variables will wipe itself out. So when I take a look at b here, I can see that I've got a positive 5x and a negative 5x. Well, those are going to wipe each other out. They're going to disappear. We're eliminating that x term, or x variable. So in these ones, I'd have negative 2y and a positive 3y. So that gives me a positive 1y. And 9 minus 11 gives me a negative 2. Nothing too much to do with that. It's already solved now for y. And I can take that and sub it into any equation I want. Oops, I forgot to number them again. I'm going to sub it into, I don't know, equation 1. You could pick equation 2 if you thought it would look better. So 5x minus 2 times negative 2 equaling 9. Maybe the other equation would have saved me all these negative signs. I don't know. So I'd have 5x minus positive 4 equaling 9. Subtract 4 from both sides. I get the 5x equaling 5. And solving for x, I get that x equals 1. Again, this is a consistent system. I have 1 and negative 2 as that ordered pair. One more to do here on the page, and again, these are all primed to work out. We are solving through the addition method. What we're looking for is one of the variables will wipe itself out when we add these vertically. And so here I can see I've got a positive x and a negative x. Well, those x's are going to eliminate. And so then I would have just a y in my equation. So moving on, I have negative 2y and positive 3y. So that'd be a positive 1y equaling 8. I can take that now and sub it into any equation I want. I'm going to say number 1. Oh, and I forgot to number them again. My goodness, always number them first. That's what the instructions say. So in this one, looking at number 1, I'd have an x minus 2 times 8, because that's what I've got my instructions to do here, equaling 9. X minus 16 equals 9. Adding 16 to both sides, I get that, wow, this is big, x equaling 25. So again, it's a consistent system. I have an ordered pair of 25 and 8, which is where those two lines would intersect, and that is the x and the y values that would make both of those equations true. So the next page, things don't work out quite so easily. In these ones, you need to do some work to make it so that one of the variables disappears. You have to know how to do that magic in a sense. And so in system 1, I've got equation 1 and equation 2, and I can do anything I want to these so that within the rules, so that I have that case where the two coefficients would make it so that one of the variables disappeared. So what I'm going to do when I take a look at these two in equation 1 and equation 2, I can see that I have a positive y up here and a negative y down here. So because they're opposite signs, I'm going to focus my attention on that y variable. In this one, if I took and multiplied equation 2 by 2, I'm going to get to a -4 on the y term. So if I do that, I can't just multiply the y term by 2. I have to multiply everything by 2. So I get a reworked version of equation 2 as 6x minus 4y equaling -44. I just bumped it all up by a factor of 2. I'm going to copy out the first equation here because now what I've got is this bit where I've got these two matching. Okay, I've got a positive 4y and a negative 4y. I had to make it so that it worked out that way, and I did it by multiplying that second equation by 2. So now that we've got that, it's going to work out if I add these two vertically. If I add these two vertically, I'd have 7x. My y's would eliminate each other, and I'd have a -42. Solving for x, divide by 7, and I get that x equals a -6. Now that I have that one variable, I can take and sub that into any of my equations. I'm going to sub it into equation 1. So I would write -6 for my x plus 4y equals 2. I'd add 6 to both sides. You could have subbed in with brackets. I'd get 4y equaling 8. Divide by 4, I get that y equals a 2. And from all of this, what I can put together is that it is a consistent system, and I've got the point -6 and 2 where these two lines intersect. So that is the value of x and the value of y that satisfy both of these equations. All right, so let's take a look at D because it's sitting up the top there. I am going to remember to number these two equations. And when I look at them, if I'm going to solve them with this addition method, I need to have it so that one of the variables wipes each other out. So I'm going to take a look at my y terms. It doesn't matter which terms you want to look at. Again, here I've got a negative and a positive. Because I have a negative and a positive, that means that I can treat one of these equations if I want by some value to make those coefficients match but be opposites to each other. So I'm going to take equation 1 and multiply it by 2. That's going to allow me to rewrite equation 1 as 2x minus 4y equaling 6. I'm going to copy out equation 2 because I've monkeyed with my y variables, hopefully, so that they disappear. And when I add these two vertically, my y variables sure disappear, but if you take a look, everything else disappears as well. And so my next statement would be that 0 equals 0. 0 equals 0 is a line of truth. And if we think back to what the line of truth meant in an algebraic approach to solving systems of linear equations, that means that my system is dependent. It means that there is an infinite number of solutions for this. If I were to take these two equations and put them on the graph, they're actually the exact same line. They just look different. Okay, so let's keep going on these. Sometimes it's that choose your own adventure that's kind of hard to crack into these. Like, how are you going to treat the two equations so that you get one of the variables to eliminate or disappear? So looking at E next, because it's next highest on my page, I'd have equation 1 and equation 2. And here, one of my first things I was looking at was having one positive and one negative coefficient on a variable. Well, here I don't have that, but I do see that I have a 3 and a 9. And so if I want to, I can take this first equation and not just multiply it by 3, but multiply it by -3. And so if I do that, I would write it out as -3x minus 9y equaling a positive 6. I'm going to copy the second equation, so 3x plus 9y equaling a -6, and I can add these two again vertically. take a look at what happens. Again, we're down to this point of 0 equaling 0. So once you get to that point, we've seen these kind before because we've done other algebraic approaches to solving systems of linear equations. Here again, I would say it was a dependent system because of that line of truth, and there are actually an infinite number of solutions to this system. Okay, a few more. And again, I think that the trickiest bit of this stuff is deciding what are you going to do to these equations so that you can make one of the variables disappear. So looking at C and looking at these ones, usually what I look for is opposite signs here. So because I have opposite signs here, if I could make those two coefficients match, that would wipe out my y variable. If I took the first equation and multiplied it by 2 and the second equation and multiplied it by 3, and maybe I should do those as dots. I don't know why I'm doing x's all of a sudden. In that one, I could rewrite this equation out. I could have 8x plus 6y equaling 22. And the other one, the other equation, multiplying everything through by 3, would have 9x minus 6y equaling 12. So now that I can add these ones vertically, I am going to have my y terms wipe out here, or my y variable wipe out. I'd have 17x equaling 34. Solving for x, dividing by 17 on both sides, I get that x equals 2. And now I can take that x equaling 2 and sub it into any equation I want. I'm going to take and sub it into equation 1. So where I see the x in equation 1, I'm going to write in a 2. So 4 times 2 plus 3y equaling 11. Solving for y now, I'd have 8 plus 3y equaling 11. Minus 8 on both sides. I get 3y equaling 3. Thought I was going to get a fraction there for a minute. And I get that y equals a 1. And so again with this one, rolling it back together, understanding that all that work has told you that it's a consistent system. I think the book doesn't always label it as consistent, but we do have this ordered pair that is the solution to this system. Last one here. In this kind of choose your own adventure bit, we've got equation 1 and equation 2, and I can really choose anything I want to try and match the coefficients. And so I'm going to maybe focus on the x term this time. I have a positive up here and a negative down here. I would take the first equation and multiply it all by 2, because that's going to give me a positive 6x, a negative 2y, and an 8. Remember, everything has to be multiplied by that value. Okay, then I'm copying the second one because I think I've matched my x terms here, or my x variables. And so now when I add these vertically, the x's are going to wipe themselves out, and I'd have 0 equaling, 3? That is a line of garbage. That tells me that that is not the answer to my system, but that my system is inconsistent. And that there is no solution to this. If I were to graph those lines, they would be parallel lines. They share the same slope. They're never going to come together. There's no value of x and y that would make both of them the same, or both of them happy. Top of the page, we have one last one. We've got equation 1 and equation 2. There's lots of different choices that you might make to make this one work. I'm going to take the second equation and multiply it all by a negative 5. So that would give me a negative 5x and a negative 15y, and equaling a negative 15. The top equation is that positive 5x and the positive 15y equaling 20. I've done what I was trying to do in matching my coefficients. In this case, I have 0 equals 5, and that doesn't make any sense at all. That is your line of garbage. That's not your answer, but it's your evidence that tells you that this is an inconsistent system and that there is no solution for this system of equations. So the last little bit with this, I think, is worthwhile to come up with a bit of a summary, if you will. So we have I'm going to do the summary at the bottom, then I'll go back and finish that. So the summary of this chapter 8 so far is that we had 8.1, which was graphing. Then I did 8.3, which was solving with substitution. And then we did 8.2, which was solving through addition. These two are both the algebraic approach. Because you can imagine, especially with my messy notes, that sometimes graphing isn't precise enough. So we had these three different options for solutions. So we could have a consistent system, where we had an x and a y value. We had a unique solution. We had a dependent system, where we had an infinite number of solutions. And we had an inconsistent system, where there were no possible solutions. So solving through graphing, when we had this consistent system, that meant we had two lines that actually intersected at some point. They intersected at this x, y point. When, again, we were solving through graphing and we had a dependent system, that meant that we put one line on the graph and the other line on the graph, and they were actually the very same line. And when we were solving through graphing and we had an inconsistent system, we put one line on the graph, then we put the other line on the graph, and they actually ran parallel to each other. In the algebraic approach, in the consistent systems, those were the ones that were all a lot more work. So we had to solve for both variables, right? Solve for x, so x equals, and then y equals, right? In the dependent and inconsistent systems are pieces of evidence for these ones. The dependent system were the happy ones. They were the easy to please. We got a line of truth here. And it didn't matter what that truth was. That was your evidence that your system was a dependent system. There were an infinite number of solutions. In the algebraic approach, when we got down to that line of garbage or nonsense, if you like, those were the hard to please ones. That was your piece of evidence that your system was an inconsistent system. So with these three different ways of solving, there are different systems of equations that are already kind of set up. Now these don't necessarily work out that easily. So we want to just go through with these ones and decide. So, you could graph any of them, but generally what's wrong with graphing? Is that it's imprecise, and so it's not always practical. And it's not always 100% accurate, especially with my approach to drawing graphs. And so given that we're not going to classify these systems solving through graphing, even though it's a legitimate way of solving, we're going to choose which is the most appropriate way to solve these systems, because it doesn't really matter how you solve them, you get to the same answer. But sometimes they're set up to be solved better through the addition or the substitution method. So those are the two words, those are the two options that we have. In these ones, if I were to use the substitution method, I'm going to end up in a world of fractions. And so because I have coefficients everywhere here, that means that it's best suited for the addition method. And again, not to say you can't use the substitution method. If I take a look at the example B down here, B, my second equation is already solved for one variable. So that makes it really easy to solve through substitution. Again, with these ones, when I take a look at all these messy coefficients, if I were to take and isolate one of those variables for the substitution method, I'm going to be a world of fractions. And so I would solve that one with the addition method. deciding how to bump it up. Or look, you can see that the negative 9y and the positive 9y would just eliminate each other. So without too much work at all, you'd be partway through your addition method, or partway through solving this system. The last one, if I take a look at that, I can see that the second equation is already solved for one of the variables, so that primes it and makes it quite simple to use substitution as a strategy for solving that system of equations. So now that we have the mechanics down, the next video is going to be about word problems in chapter 8.